Hello and welcome to this discussion about scatterplots and simple regression lines. In this video we'll be talking a little bit about scatterplots and how they're made, as well as the regression line that is created from that scatterplot and how to interpret both the slope and the intercept. So let's go ahead and get started, and what I'd like to do is show you some of the basic features of a scatterplot. Basically with a scatterplot, what we're doing is we're plotting two scale variables. And we are plotting the relationship between them. Typically, those two variables are designated x and y, and x is usually the exposure or the predictor variable, and y is typically the disease or the outcome variable of interest. So let's imagine that we are creating a line, and I'm just going to give myself a few points here so that I can draw a nice straight line. In linear regression, we're always interested in that straight line. And so if this were our regression line, this regression line is just like any line that we learned about in geometry back in high school. This line has an equation that defines it. And so if that line ended up being our regression line, we would say that y, the value of y, is equal to the intercept plus the slope times x. And specifically for this line, the intercept is defined as the value of x, the value of y when x is equal to 0. So we'll just say that these grid lines represent 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on. Let's say this is equal to 1, 2, 3, and so on. So the y-intercept is, this intercept right here is equal to the value of y when x is equal to 0. And so where x is equal to 0, we can see that the value of y is equal to 1. And so for this line, y would equal 1 plus the slope times x. So let's calculate the slope here. Slope is equal to rise over run. And in this case, we can see that for every 1 unit that our line goes up, it goes across by 2 units. So our slope by definition is rise, which is 1, over run, which is 2. And so that is 1/2. And so we could calculate the value of y for any given value of x. Let's say that we have a value of x is equal to 10. So we would plug in 10 here for our x variable. Y is equal to 1 plus 1/2 times 10. And that is equal, 1/2 of 10 is 5, so that is equal to 1 plus 5 is equal to 6. So let's check and see if we got that right. So when x is equal to 10, y is equal to 6. And why is this important in public health? Well, if we have these two scale variables and we want to see the relationship between them, we want to see all kinds of things about that relationship. If we know something about this x variable, about our predictor, then can we predict what the disease or the outcome is going to be for that particular relationship? And so that's how we find and interpret the slope and intercept. And so here in the equation is where our slope and intercept are. And here on the actual scatter plot itself is where we would find both our intercept and our slope. And so whether you're given the scatter plot or whether you're given this equation, you should be able to find that slope and intercept. Now, scatter plots aren't usually just a collection of little dots in a row. Usually scatter plots have a little bit more variability around the line than that. And so let's say we imagine our scatter plot to look something like this. And actually the scatter plot would be created after we had plotted all of these dots. We don't generally put the line there and then put the dots there later. And what you'll see is that our the scatter of the scatter plot tends to create this sort of elongated oval shape. And that's pretty typical of a lot of relationships, but it's not the only kind of shape that can be found. Sometimes the scatter plot just shows a relationship that is there's really kind of no relationship there at all. If the dots just form this random glob that ends up being kind of more of a circle, that can also be the kind of relationship that we see. And in this case, we would say that there really is no relationship. If we were to try to draw what over here, we've drawn this nice straight line kind of through the middle of that glob so that it's evenly above and below all of those different dots. Here, we could actually draw a line pretty much in any direction, and it would be equally representative of all of those dots. And so here we really don't have a relationship between x and y. So that's an example that there's really no relationship. Any of these lines that goes through that circle really are just as good as any other line. So let's come back to our original graph here. And it's important to understand the language of something when you're studying it. So here I want to show you something that's called a residual. And a residual basically is just represents the distance that any one of these dots is away from the regression line that we end up forming. And so each one of these has a vertical distance away from that line, and that is called a residual. Well, this particular line that we've drawn here, if we did it correctly, has been created specifically to meet to be as close as possible collectively to all of these different dots. Now, granted, any individual dot may not rest on the line, but collectively this line is as close as possible as it can be to all of the dots overall. And that's actually how this line of least squares is decided. Where are we going to put the line? I could theoretically, and I'll put it in a different color so it's not confusing, I could draw a line up here, and that is not collectively as close to all of these dots as the original one that we put right here in the middle of the cloud. We want that to go as close as possible through the middle of the cloud. This blue line up here is farther away from a lot of the dots, and it's not very close to most of them. So basically what the computer does in order to place this line in the right location is it calculates all of these distances, and it finds the line that will collectively be so close that if we were to take all of these distances and square them, then this is the line that creates the smallest number out of all of those collective calculations. So the least squares means that I take all of these differences between the observed values and the potential regression line, and I square them, and I find the number that is the absolute smallest, and that's where that line ends up going. And so if somebody were tempted to put the line somewhere else, all of those squared distances would end up being farther away from that other potential line. So the regression line, the simple regression line, is placed in a location so that it minimizes the residuals, and that's how we find that best fit line. Now, one of the things that is important about scatter plots is that anytime you're doing a regression or a correlation, it's very important to look at the scatter plot. And the reason for that is that it may be possible that instead of having either no relationship like we see over here or some kind of nice linear relationship, we may end up with something that actually looks more of a curved line. And sometimes it can curve all the way back down or be a J shape. And so the best fit line for that particular relationship is a curve. And so simple linear regression or a correlation coefficient will not be a good description of that, because when we look at linear regression, it's trying to find the best straight line through that data, and it really is not fitting all of the data very well when we end up trying to fit a curved shape to a straight line. Also, another thing that might happen is that we may end up with a group of data, and let me see if I can draw this pretty well. We may end up with a nice relationship, and then suddenly somewhere there's this outlier down here. And what that does to the overall line, sometimes depending on how many data points there are, is that can pull that regression line down towards that one outlier. And so then this regression line isn't really fitting the bulk of the data. That line really should go more up through here. So we're looking for outliers. We're looking for shapes that really are not best fitted by a straight line. And so those are some of the kinds of things that can happen with scatter plots. When we're describing a relationship between x and y, there are a few things that we can use to describe it. First of all, we need to describe the form. And the form can be either curved or linear. And specifically with simple linear regression, we're looking for a linear shape. We can also describe this in terms of direction. And if the scatter plot is as it is over here, this is a positive relationship, whereas as x increases, y also increases. In other words, this line goes up and to the right. It's also possible to have a scatter plot that is down and to the right, and so as x increases, y actually decreases, and that's called a negative relationship in terms of direction. We already talked about outliers. The other thing that's important about scatter plots is the strength. And this is a little bit of a difficult concept, because the strength of the relationship doesn't have to do with how steep the slope is. It has to do with how close all of those dots are to a regression line. And so if we have all of the dots falling exactly on, whoops, that's not even linear, let's say it is. If all of the dots fall exactly on the line and it goes up and to the right, the strength of that relationship is equal to a positive 1. So that's as strong as it can be. If we have a similar relationship where all of those dots are somehow kind of down and to the right, then that is described as equal to negative 1. And so those are all exactly on the line. Now, to the extent then that there are a few that are farther away from the line. Both of these would probably be approximately equal to 0.9 or equal to negative 0.9. And so they're still pretty close to the line if we were to draw a little football shape around them. But they're starting to get more spread out. And these can actually be at any angle. If we were to have a relationship that is more like this, and it was spread out about the same amount around this line, that is still equal to negative 0.9. So the slope is not what determines that strength of relationship. And that this strength of relationship that we're describing here is called the correlation coefficient. And so that strength of the relationship, it has to do with how close the dots are to the line. It doesn't have to do with how steep the slope is. And remember, we talked about how steep the slope is. So here is an example over here where we drew this, that it just forms literally a circular cloud. The strength of this relationship is 0. So in terms of the strength of the relationship, it actually goes from -1 all the way up to 0, and then from there all the way up to +1. And so anywhere along that scale of 1 to -1, anything over here has a negative slope, and anything over here has a positive slope. And so that relationship can be in either direction, and the farther you get away from 0, the more and more and more those dots cluster closer and closer to the line until they are perfectly on the line at -1 and +1. So those are some of the interesting features and important aspects of the scatter plot and the simple regression line. Thank you so much for joining me.